Alicia, what was the thing called transfer waves? I mean, what is so special about it?
Um, the wave particle travels perpendicular to the no, the vibration is perpendicular to the direction of propagation.
Propagation of wave. Remember one thing, when you're talking about transfer wave, you normally don't use the word vibration because here the particles
Okay.
not vibrating, but actually moving. Up and down, we don't
Okay.
call it vibration. So
So
we call it
it moves perpendicular to propagation.
propagation, wave propagation. Right?
Okay.
Example,
Um, example is like water wave, sound wave.
okay, and light. Light is also one of
Okay.
them, right? And light waves.
Yeah.
Then we had gone through some of the characteristics of the transfer waves like crust. Zoha, can you tell me what is crust?
Crest is the peak of the wave.
Not
The
peak, the upper part from the mean position. Peak is just this one. You can't say peak, you say upper part from the mean position. Okay?
upper part of the mean position.
And trough is the lower part from the mean position. This one. Okay. Now crust and trough is like that. Then you have a time period. What was the time period? Yes,
The time required for one complete wave.
to pass through, right? Which is in
Yeah.
seconds. What about frequency?
Seconds.
What?
Frequency?
Number of
Number of
waves
waves passing a
through
point per second.
in 1 second.
Its SI unit is 1/second and 1/second, which we called as
Yeah.
hertz, right?
Mm-hmm.
What about wavelength?
Distance between two consecutive crests or troughs.
Yeah. What about displacement?
The vertical distance of the particles in medium
From the
in
mean
the rest
position. From the mean
from the
position. From the mean position. That's important. Mean position or rest position, whatever. And what about amplitude?
max displacement
Mm.
from the rest position.
Yeah. One more thing, there is a relationship between a frequency and a time period, that is T is equal to 1/f. If you know time period, you can reverse it, you will get frequency. Or if you know frequency, you reverse that, you will get time period of one wave. All right.
Okay.
One more formula which is in this course is V is equal to frequency lambda, where V is the velocity, F is the frequency, and lambda is the wavelength. So if you know any two of these things, you can easily find out the third variable or third physical quantity. So these two formulas will be used during all of this, waves and sound thing. Okay. Now, once we went through the one we have already gone through, let's start with the longitudinal wave. Longitudinal wave. First of all, I'll show you what kind of wave you will get it. Now, what exactly it is, I need to explain that to you. First of all, let me show you a spring here. Then you will in a better condition to understand that. Okay, see this. If you check this out, actually, wave in the spring. Okay, this one. Check. Now, this is your basically, what is it? Don't let this anytime. Let the feelings run over. I didn't say this. This one. Now, check this out, what exactly it is. Actually, this is a spring, which actually you had it. My question is here, when you actually stretch the spring and you leave the stretch, like for example, your spring is like this, right? When you stretch it,
Yeah.
it will be like that.
Yeah.
What if you release it? What will happen? Will it close automatically and come to its original shape directly?
No.
Then what happened?
Um,
The first thing is,
whatever
instead
you
of,
leave off,
I tell
it
you what,
will start to.
yeah, first thing is, once you release it, the force will take that spring to a position where the spring actually compressed. Then at this point again, the force will take that spring to be elongated. This thing just, that happens for once or twice or thrice, and then after some time, your spring actually reaches to its actual shape. The shape of a spring in which there is no frequency or there is no disturbance, no wave, we call that position as mean position. Now, if you check it out, initially when you expand it, it was elongated. Then when you released it, it actually shrinks. Then it's elongated, then it shrinks, then it's elongated, then it shrinks. I mean, shrink like that. Now see that. You will see some point here. Spring shows the particles are showing distant. Here the particles are showing close to each other. Again, here the particles show a bit distance. Here the particles are showing close to each other. Again, here distant. So if you see that particles are this position, particles are closed. That position, particles are far away. Then this position, particles are close. Particles are far away. So if you see that particles are coming closer to each other, then particles are getting far of each other, then close to each other, then far to each other. Now, my point is which way the wave motion is from left to right and which way the particle motion is. Yes, initially it was perpendicular, right? Here, the direction of the motion of the wave and the particle motion will be what? Parallel or perpendicular? Parallel. So, first thing is in longitudinal wave, particle of the wave travel parallel to the direction of the propagation of the wave. So here the particles are actually moving parallel to the direction of the propagation of wave. Now here, if you see that some areas are where the particles are very close to each other and some where are particles actually a bit far away from each other. Those areas where the particles are far away, we call that part as a rarefaction. And those areas where the particles are close, we called it compression. So compression and rarefaction. Zoha or Alicia, actually,
Yeah.
we are recording, so if there is no background noise, that would be nice, right? Okay, so basically, now important factors. Instead of compression or rarefaction, we do have, what do we have it? We have rarefaction and the compressions. And what is compression here then? Compression is the area or the region, let me write it. Compression, it is the region in the longitudinal wave when particle of the medium are close to each other. That is called compression. The other one is rarefaction. So what will be the definition for that?
It's the same thing in the region of the longitudinal wave where the particle of the medium are far away from each
Far away.
other.
Yeah, longitudinal wave when particles of the medium are far away from each other. In this definition, I mean, while you're talking about longitudinal wave, instead of talking about the wave, we talk about vibration or oscillation. So what will be the time period here? Time required to pass one vibration or oscillation from a point the unit is seconds. What is the frequency? Number of waves, in this case, number of vibrations passing per unit time. The unit is again hertz. What will be the definition of wave here? I mean, not wave, I mean wavelength. Previously, it was distance between two consecutive crusts or two consecutive troughs. Here, it will be distance between two consecutive compressions or two consecutive rarefactions. So you can say that wavelength will be distance between two consecutive compressions or rarefaction. Again, it is denoted by lambda and the unit is meters. Displacement and amplitude will be the same. Here, the mean position will be a position when you didn't stretch the spring. That is your mean position when actually there was no disturbance produced. Any questions?
No.
No.
Okay.
So vibrations are the same as waves.
Yeah.
Comparing the two.
Because actually,
And
yeah.
compression or rarefactions are the same as crests and troughs.
But definitely, yeah. But here it's in longitudinal wave where crust and trough are in transfer waves. What are the examples of that wave? Sound waves. Sound is the best example for them. Waves produced in a spring, or you can say spring waves. Sound wave are the best example, by the way. Now quickly summarize it and let's have a differentiation or difference between transfer waves and so make a column of transverse waves and longitudinal waves. Alicia, what is the first difference between these two?
The direction of like propagation, the wave motion.
So what is it?
Also, transverse wave, it's perpendicular,
Yep. And
and for longitudinal, it's parallel.
absolutely. And what is the second point? Example? Any example which is in your mind for transfer waves and longitudinal wave? Zoha?
As an example for each,
Yes.
X-rays for transverse and water waves.
Yep. Water waves or light, you can say. At the longitudinal side, it will be sound waves or waves produced in a spring. Then you can draw a shape as well. That could be the another difference. And here the waves look like this. What could be the another difference for that? In transfer waves, crust and troughs are formed. In longitudinal waves, compression and rarefaction are formed. Right?
Right.
What about the last difference between these two? Fifth one. Wavelength. What is the definition of wavelength in transfer waves? Yes, Alicia. Elsia?
In transfer wave, it's the distance between like hello, it's the
Yeah, yeah.
distance between like trough and peak and peak.
Consecutive crusts or consecutive troughs.
Yeah,
On the other side, it will be consecutive compressions or consecutive
and refractions.
rarefaction. This is all summarized of what we studied in transfer waves and longitudinal wave. Any questions
Yeah.
regarding this topic?
No.
Okay. Now let's move further then. And for this time, we have to actually go to the main topic. And what is it? Let's see. Where is it? Diagram show a diagram. Okay. Let's talk about this. Save my pages. Not this one. Vector scalar, it is. All right. Now there is some important things which we will be discussing here, and that is related to your now the important thing is one few more things, and then we actually jump to another one. Longitudinal wave we have done, transfer wave we have done. This definition we have sorted out. Okay. One small topic left is polarization. Now, what is called polarization? Particle oscillations occur in only one of the direction perpendicular to the direction of the wave propagation. So basically, if just one direction, that will be polarization. So polarization can only occur in transverse wave. This means transfer wave oscillate in any plane perpendicular to the propagation direction. When transfer waves are polarized, this means vibration are restricted to one direction. Now, this is very interesting, actually. I will explain you in the diagram, you will understand this. See, first of all, for polarization, this is important that you are talking about the transfer waves. Reason is, for polarization, it is important that whatever the wave is traveling, it should be perpendicular to the plane. So be a perpendicular or movement in the perpendicular direction is necessary for polarization. That is the reason polarization can only occur in transfer waves. Now, you tell me one thing, when waves are actually moving, can wave be just moving in one direction or one plane, or can it be multiple planes? Vertical, I'm talking about. There are 3D planes, right? If I talk about it, for example, let me give you an example, you will understand. If you consider this one as a path, wave can travel this way. Wave can travel z-axis and x-axis. Wave can travel z-axis and y-axis. It has to travel perpendicular, right? So it can be in any plane, but it should be perpendicular to the plane which actually is running through. So what polarization means is it will restrict all the waves to actually pass through in one direction. In that way, when it restricts that, all the energy is actually going in one direction. So this vibration are still perpendicular to direction of propagation, energy transfer. So energy is transferred. Now, what is this significant? That's what I've told you. Normally, this happens in the sort of, so many things it happens into. So this difference between unpolarized and polarized waves are shown in the diagram. Now check this out. The wave which is shown here, it is unpolarized because it is spreading in all the direction. While here, if you see that, it will only and only showing one direction, that is perpendicular to the direction of the propagation of wave. You tell me which wave actually passing most of the energy, the polarized one or unpolarized one?
Say again.
What my question is, in unpolarized one, the wave means the energy transfer as well. In a vertically polarized one, the wave is also transferring the energy. But which wave is actually transferring the most of the energy which we want it to be? Unpolarized one or polarized one?
The polarized one.
Because what we needed that at output side, we get the most of the energy. So if your energy is polarized, and it actually just transfer energy in all the direction, then our basic aim to actually passing the energy from one point to another point is went in vain, because the reason is unpolarized wave send the energy but in all the direction, so you may not reach the exact energy you wanted at the output side. While if you do the polarization thing, the energy transfer will be the best energy we can have it. So we always do the polarization thing. And while we do the polarization thing, the energy transfer will be in only one direction. Actually, in this way, the maximum amount of energy will be received at the output side. Understood? Yes.
Yeah.
Same way as the horizontal polarization is, we got a vertical polarization is, we got a horizontal polarization as well. This is also perpendicular to the plane. Remember that it should be in one plane. Where it can be in horizontal plane, it can be in vertical plane as compared to the direction of the propagation of wave. All right? Now,
Can
if
you explain why polarization will help get the maximum amount of energy?
okay, no problem. Do you see an antenna in your life? I'll show you the antenna here. Antenna. This is your antenna, if you see that. Especially, I'm talking about this one. I don't know you ever see that or not. If you see the antenna, you can see these, sticks sort of item, these ones. I'm talking about these ones. Why they are always straight? Why not they are showing a curve or anything? Yes, any ideas?
Because they only want waves in that direction.
That's what I said. Actually, the waves which are produced for the communication, these antenna things, these sticks, actually trying to polarize that particular waves in one direction so that they will get most of the energy, or wherever they are transferring the energy, they send most of the energy. Because if they don't polarize, I mean, they don't polarize the wave, or wave which is coming to them are not polarized, then you may not get the maximum energy. So actually, the channels we are getting may not be that much clear, because energy which we receive may not be that powerful, so that we can easily see channels best quality. So it is important to polarize the, you know, transmission coming from main satellite or something. And how do we polarize it? We should put these sticks, which I just talked about, in one direction. It can be this direction, which is they are, or it can be in the horizontal direction as well. Like if I show you in the other antenna, you may find this in a different direction. Like for example, here, if you see that, here the direction is a bit different. Here the direction is different. So why they are like this? Because they are trying to polarize the waves. And polarization may occur in two directions. It may occur in vertical direction. It may occur in a horizontal direction. Right? So
Mm.
let me show you antenna wave polarization. Check this out. This is your antenna. Now, if you just see that those sticks, they just polarize the wave in such a way that here the waves are passing in just horizontal direction. Sometimes they are made in such a way that they are polarizing the wave in vertical direction. But remember one thing, the important thing is whatever they do, whether in horizontal direction or perpendicular, I mean horizontal direction or in vertical direction, this causes the maximum energy transfer in one at one side, you can say.
Okay.
Okay. So this is what the meaning of polarization is. Okay. Now here, longitudinal wave cannot be polarized. This is because they oscillate parallel to the direction of traveling. So you cannot polarize it because they are not showing perpendicularness, because only those waves which are perpendicular can be polarized, right? Now another very important point. This is showing a picture. Waves can be polarized through the polarizer or polarizing filter. This only allow oscillation in certain plane to be transmitted. If you want your waves to be transmitted in a certain plane, then this polarizer will be used. It takes all the wave going in different direction, and then it do in such a way that the waves will be polarized and will be transmitted in one direction. So those sticks which I just showed you in antenna, they actually worked as a polarizer, and they actually transmit energy in one direction.
Okay.
All right. So that is the job of those antenna things. This is polarization around rotated at 90-degree. That is at a different direction, but polarization occurs like this. Now, if you read it, only unpolarized wave can be polarized. When the polarized wave passing through the filter with the transmission axis perpendicular to the wave, none of the wave will pass through. They just give you a thing. So, of course, if you are doing it parallel to the direction of the wave, nothing will be passed through. Now, check this out. This is the observer. This is the transmission. Here, the waves are unpolarized, light source. Now, this particular polarizer took the light wave, and this is your polarized wave. It can be a light wave, it can be, you can say, a transmission wave, it can be anything, right? When both polarizer have the same transmission axis, the intensity of the transmission light is at its maximum. As I just told you, that's what we wanted. All right, understood?
Yeah.
Now here, if you see
Yeah.
that, previously the polarizer are in the same direction. That one was oscillation in all the direction. Here it is perpendicular, here it's vertical. So oscillation in one direction, that's fine. But once it's passed through, nothing gonna pass through. So it means that we reach to one further conclusion that if there are two polarizers and light passes through one polarizer in one direction, and it's not possible that a second polarizer should be in different direction. Otherwise, you will not get a single polarized wave at the output side. You should have both the polarizer in one direction. Then and only then you will get a polarizing wave at the output. Okay.
Okay.
Now this is a small diagram. The maximum intensity will be shown when if there are two polarizers, both have the same direction, and that is your maximum one. And this is the minimum one because it is shown at the 0 degrees. A worked example is here. Which statement below describe a situation in which polarization should happen? Radio wave pass through a metal grid. Surface water wave are diffracted. Sound waves are reflected. Ultrasound wave pass through a metal grid. Surface water are diffracted. Remember that it's nothing to do with diffraction. Diffraction means bending from the sharp edges. We will be studying this in a few moments. The C part is sound waves are reflected. It's nothing to do with reflection or refraction. D part, ultrasound wave pass through a metal grid. So basically this cannot be happened because ultrasound or sound wave, they are all longitudinal wave, and this happens only and only in transfer wave. So A part is the best option. Okay, any problem? Or
No.
any question? No.
No, there's no question.
Good. Now application of the polarizers. Polaroid sunglasses are glasses contain lens with polarizing filter with transmission axes that are vertically oriented. This means glasses do not allow any horizontal polarization lights to pass through. When light is reflected from the reflective surface, the surface of water or a wet road, it undergo a partial plane polarizer. Now they give you basically an example of the application of polarizer. Here, if you can see that horizontal polarized light is blocked and polarizing sun only transmitted vertical light. So vertical polarization light passes through. What happened when horizontal polarized light is not, when it is blocked? You can see clearly, simple as like this. All right. So this is one of the example of the polarized sunglasses. They are a bit expensive glasses. If you read it, this one, when a light, now this one, what actually is happening and how actually this helps us to actually get the best result. They say that when the light is reflected from the refractive surface, the surface of water or a wet road, it undergoes partial plane polarization. This means if the surface is horizontal, a proportion of the reflected light will oscillate more in the horizontal plane than the vertical plane. Therefore, polarized sunglasses are useful in reducing the glare on the sun surface of water, as the partial polarized light will be eliminated by the polarizing filter. As a result of this, object under the surface of water can be viewed more clearly. So very simple. Especially this happens when you will have a very bright sun. I don't know you ever noticed that or not. In a normal glasses, it's very difficult to see through the water surface. The reason is you will find a shade of the light as well. Because actually light is coming where it was unpolarized light. So light is coming in horizontal polarized form. I mean, in the position of horizontal one, as well as in vertical position. Okay. So what we do, we made the glasses in such a way that it will just receive the light in only one direction, one polarized direction. This way, our clarity will be more and more visible, or you can say our visibility will be more and more clear. All right. This is related to the
All right.
now Polaroid photography also. Polaroid camera works in the same way as Polaroid sunglasses. They are very useful for capturing intensified color and reducing glare on the particular bright sunny day. Again, this will be used to actually capture the best result you can have, and definitely to reduce the brightness of sun on that sunny day. Polarizing filter also enable photographer to take photos of the objective underwater. So this is also used for underwater photography as well. This is because the light reflected on the surface of water is partially polarized in the horizontal direction or plane. This glare is eliminated by the polarizing lens. However, the light from the underwater object is reflected by the surface of water and not reflected, so it is not plane polarized. Therefore, the light from the underwater object is more intense than the glare and is shown up much more brighter into the photo. So they just told you, I mean, this all explained that why it is more clear if you take a picture from the water. So this is the way they've just written it. They are just the examples of polarization and everything. This is non-polarized. Check it out. Can you see the shade here?
Yeah.
This shade is because actually it's not polarized properly. Or it will be, you are getting the perpendicular, I mean, 90-degree polarized on x-axis as well as on y-axis. That's the reason you are finding shades as well. On the right hand side, it is polarized, or you can say polarized filter, so that actually the shade will be removed and your visibility can be more and more clear. Understood?
Yeah.
Now check this out. They're showing you the example of the, that antennas as well. Radio and television services are broadcast either horizontally polarized or vertical polarized. Therefore, the reception area needs to be mounted flat or on its size. The particular orientation of an aerial will depend on the transmission it is pointing towards and polarity of the service being broadcast. So the if for example the signal is transmitted in a horizontally aligned aerial, then your aerial should be horizontally polarized system as well. Like if it is horizontally polarized, your antenna should be horizontally aligned. Otherwise, you may not get the proper signals. If it's vertical, then your aerial should be vertically aligned aerial. Understood? Or any problem in this?
No,
Understand.
this is understandable.
This is all polarized, what we have in our course. Now, let's start with the stationary. Now, what do you think a stationary wave is? That's what the point is. What do you think a stationary wave is? Any ideas? Yes,
A wave that doesn't move.
a wave that doesn't move. Okay. If it doesn't move, then, I mean, what exactly it does? A wave which doesn't move.
As in it is fixed in place.
That is one.
It
That is one of the points you're saying, absolutely. But if it's fixed in place, how can that be a wave? I mean,
It stores energy instead of transfer.
Yes, that's one of the points. You are absolutely right that it stores energy. And storing is because it actually stays at one point rather than it's moving. But my point is, if it stores the energy, how does it happen? That's what my point is.
Because it has
By
nodes.
superpositioning of
No.
two progressive waves.
See, now at this point, we actually need to say to actually show you one thing. Check it out, the first wave, which is actually shown here. If you check this out, the first wave, even though one part is fixed, this part is fixed, you actually fixed to some wall or something. When actually you try to, what you call that, you try to actually create a disturbance, you will get a wave, right? That wave. My point is, if you check this out, this is a outward pulse going this way, going this way. What happened when the wave will come back actually? Because what happened as the wave goes to this end, it will reflect and it comes back. Am I right?
Right.
So point is, if it's coming back, it means it's stuck to one place. It actually do not progress further because it has a fixed point, at least one fixed point. Most of the time, it has two fixed points. So it will not even go to any other place, but it will continuously moving in that particular circle. It go there, it reflect from here, come back, then reflect from here, go back, reflect there. So wave will be in a sort of a loop. All right. So basically, what exactly is a stationary wave here? A standing wave are produced by the superposition of the two waves of the same frequency and amplitude traveling in the opposite direction. So what are the conditions which are necessary for the standing wave? The first condition is that the waves should have a same frequency. It's definite that you are talking about wave in a string, right? And if, for example, they are fixed from both the places, it will give you the same frequency. The reason is the source is same. It's the same string. If the string is same, it will generate the same frequency. Remember that frequency of any object will never change until and unless their sources are different. Here there is one source. So whatever wave is going or outward wave is, the reflecting ray will be the same. So same frequency, same amplitude, but in opposite direction. So basically, standing waves are produced by the superposition. Now the word is superposition. Superposition is very interesting word. A principle of superposition states that if wave from two sources traveling by different route from the same occupy the same region, then the total displacement at any point in the vector sum of their individual displacement at this point. Now what does it mean is, let's suppose this is your wave. This is another wave. If this wave is passing on that wave, what will happen? This will actually launch on this wave, or you can say this wave will jump on this wave. The resultant may be having a more displacement or maybe result in less displacement. Am I right?
Right.
So this, suppose superposition means if something, it's just like in English we call it that do not superimpose your point on my point. It means that if I'm saying something and you're trying to superimpose that, or you're trying to pressurize somebody, you're giving a point or a logic in such a way that you are superposition or you're superposing something. It means you are actually giving an extra support, or maybe you're giving not a support to that question. So same way happening here. If two waves are superposed to each other, the resultant may be a huge or a large displacement, or may not be a large displacement. It may be a less displacement. So basically, your standing wave are actually produced by the superposition of two waves of same frequency and amplitude, but traveling in the opposite direction. How they achieve it? Simply traveling waves and its reflection. This is usually achieved by traveling waves and its reflection. The superposition produced a wave pattern where the peaks and the troughs do not move. Now, this is very interesting. Here, actually, there is no peaks, and in general, we are. I'm not saying crust and trough, but there are peaks, but they are not moving. They're just vibrating. That's what the fact is. Now, check this out. And stationary waves store energy, unlike the progressive wave, which transfer energy. Now, check this out. At this point, the things are very interesting, which needs to be explained because a new term actually arrived here. The term is called progressive waves and stationary wave. Till now, the waves we were studying are progressive wave. Alicia, what is meant by progressive waves?
It transfers energy
No, that's
and
fine.
not matter.
Actually, they transfer energy means they are continuously moving from one point to another point and to
Yeah.
another point to another point to another point to a new point. While stationary wave will be stuck to certain points. It may not be transferring actually. It will stuck at one point. So first point between as a differentiator, the first point it all the wave have same amplitude. Why? Now this is interesting actually. If I draw a transfer wave like this, that point with respect to the mean position will be at the same distance. So it means in the all progressive wave, complete progressive wave, amplitude remain the same. It will not be changed. All the points have same amplitude because amplitude means the maximum displacement from the mean position. It will never be changed. It will be same for complete wave or multiple wave in a full wave motion. All right. On the stationary wave, each point has a different amplitude depending on the amount of superposition. Now, if you see at the top, every point got a different amplitude or different displacement. And it depends on how much superimposition or superposition another wave actually jumped into. That is the first difference. The second difference is the one which you were talking about. Energy is transferred along the wave in the progressive wave. And the second one is energy is stored, not transferred. Second difference is very interesting. Points exactly at wavelength apart are in phase. The phase of points within one wavelength can be between 0 to 360. Now, this is again very interesting. You tell me what is in phase means. Anyone? Yes, what is meant by in phase?
Is it where like crusts are meeting with like crusts and trough with troughs or no?
When we say the distance between two consecutive crusts or trough, actually we are talking about a point on the wave crusts so that when you draw a straight line, it will pass like that. So these two points, these 2 points are in phase.
So is it also just when they have the same path difference?
Yes.
Or the path difference is 0?
Again, what you said?
Or the path difference is 0?
Difference is 0. What difference?
As
It's not about the difference is 0. But my point is, check it out. This is your wave, right? If I ask you, is this the distance which is lambda is? For lambda, if you really need what the lambda is, you need to find a point here and same point in the next wave. When I say same point in the next phase, I can say that these 2 points should be in phase. You can say same position, maybe in the different waves, but it should be at the same positions. Easiest way to find out that point is draw a horizontal line. Wherever this horizontal line touches, those points are in phase. So what they're saying is point exactly a wavelength, because one point comes after a complete wavelength. Because other point come after one complete wave, means one crust and one trough will pass and then new crust will come up. So you can say the points are coming right after one lambda. And those points are in phase. The phase of points within one wavelength can be between 0 to 360, because 0 to 360 means is that if I take this one as a 0 degree, then 360 is coming at this point. So basically, you will find in phase distance within this, within 0 to 360. On the other side, points between nodes or in phase. Now, this one is very interesting. What are these nodes? This is your wave technically. These points are called as nodes, and these points are called as antinode. So points between nodes are in phase. Whatever point is here, they are in phase. Points on either side of the nodes are out of the phase. If there is another, for example, wave, like for example, you may have two nodes and two antinodes here, like this side of wave. This is one node, this is other node. This point is not in phase with this one. This is not in phase. The point should be under one envelope. These points are in phase. If you go beyond two nodes, which are very near to each other, then we don't call them they are in phase. For in phase condition, the point should be within the nodes. So one by one, once again, the first point is the amplitude of all the progressive wave, or all the points have the same amplitude. While on the stationary, amplitude will depend on the amount of superposition. Second point, I told you that one in progressive wave, the energy is transferred along the wave. In stationary wave, energy is stored. In the first progressive wave, the point which are in phase comes exactly after one complete wave. And the phase of the points within one wave can be between 0 to 360. Phase means the difference between the two waves on the crust or either on the trough. One value will repeat within 0 to 360 angles. That's what that means. On the other side, stationary waves, it says that point between nodes are in phase. Between points on the either side of the nodes are out of the phase. The fourth one does not have nodes or antinodes. In progressive wave, we have compression or rarefaction, or either you have crust or trough, while in the stationary side, you have nodes and antinodes. All right. Now, next is another difference. The wave speed is the speed at which the wave moves through a medium. Because in progressive wave is actually moving in the medium. So what is the speed of a wave? It is the speed of which at which the wave moves throughout the medium, because it is moving throughout the medium, not within certain place. On the other side, each point on the wave oscillate at a different speed. Overall wave does not move. Now this is actually a very tricky thing. It's not moving, remember that. It's just vibrating. While on the other side, energy is actually traveling, so it means the wave is actually moving from one point to another point. Any questions?
No.
Yes, Alicia, you? Shall we move then? So now we have a new type of category, which is a progressive wave and a stationary wave. You know, technically speaking, most of the people do not even call a stationary wave a wave, because actually it's not a wave. It's just a superposition of one wave which is going outward and the other wave which is coming back. So actually, this wave is not even the way of transferring energy, but rather it stores the energy. That's the biggest non-definition of the wave, by the way. Again, I am repeating one by one what are the major differences. First one, amplitude of all the points in the progressive waves are same, while in stationary, amplitudes are different as per the amount of superposition. Second point exactly a wavelength apart which are in phase. All the in phase point will come rather at passing through one wavelength. And this point or this phase of a point within one wavelength can be between 0 to 360. While on the other side, the points between nodes are in phase, but points on either side of the nodes are not in phase. Then the third point is energy is traveled along the wave. On the other side, energy is not traveled, transferred, it is stored. In one, you do not have nodes or antinodes. Stationary, you have nodes and antinodes. The first one is wave speed is the speed at which wave moves throughout the medium. On the other side, each particle on the wave oscillation at different speed. So overall wave does not move. Okay, let's move on then. Now, what are nodes and antinodes? As we have just seen through, what are nodes? Now, first of all, you got a string here, you pluck it. You will find a wave goes this side and it comes back this side. Now, if you see these 2 points, which are at the, you can say at the end point, you won't find any displacement, do you? Yes,
Yeah,
so
there's no displacement.
no displacement with respect to the main position. So these points where the displacement is 0, we call them nodes. And a point which having a maximum displacement with respect to the mean point or mean position, we call them antinodes. So what are antinodes and nodes? A stationary wave is made up of nodes and antinodes. Nodes are the region where there is no vibration. Antinodes are the region which vibrates. Vibrations are at their maximum amplitude. Nodes and antinodes do not move along the string. Nodes are fixed and antinodes only move in vertical direction because antinodes are at the maximum point. The phase difference between 2 points on a stationary wave are either in phase or out of the phase. Points between nodes are in phase with each other. Points that have an odd number of nodes between them are out of the phase. Point between even number of the nodes between them are in phase. Now what they are saying is, let's understand it with the help of diagram. How many waves are there actually technically? There are 3 waves actually. If you ask me, it's 1.5 waves basically, because one complete wave is 1.5. But if you consider the full envelope, it will be 3 waves. But wavelength of this particular wave will be 1.5. Now, if you check this out, what my point is, if you see these nodes, whatever points are within this envelope, they are in phase. And whatever points are there which are not in the envelope, like here or something, they are out of the phase. So what they're saying is phase difference between 2 points on a stationary wave are either in phase. Now, phase difference means, like if I say, let's suppose this is a wave, right? And there is a wave as well. This is called How much wave is already passed, then this wave started? One wave is already passed. So phase difference of one wave is there, or you can say phase difference of lambda is here. This wave is lambda ahead of this wave. So that's what we called as phase difference. Now, what they're saying is phase difference, because in that case, you do not have phase difference. Phase difference are either in phase or out of the phase. Point between nodes are in phase with each. Points that have odd number of nodes between them are out of the phase. Point which have even number of the nodes between them are in the phase. Now they are odd. So within them, like this one and this one, all the points are in phase. But if it's even, then it's out of the phase. Generally speaking, if you got two nodes here, all the points are in phase like that. Because there can be a straight line. But if you're talking about this point and this point, no, they are not in phase. Okay, understood?
Not really.
Where do
Why
you
are
start?
those two out of phase, the two antinodes?
See, this is just a thing to understand it. Out of phase means when you're talking about a point which actually, you can say, let's suppose again, phase difference. Now, if I ask you what is meant by phase difference, we can talk about this. Now check this out. If this is a wave and this is a wave as well. Let's suppose this one. Are they both same?
No.
Technically speaking, this wave, the second wave, is half wave ahead of the first wave. Am I right?
Yes.
That halfway, if you consider it lambda, the half wave is lambda by 2. Technically speaking, the second wave is lambda by 2 ahead of the first wave. Am I right?
Yeah.
So this lambda by 2 is basically called as phase difference. If one wave is ahead of another wave, the difference between those two waves is called as phase difference. Now, in stationary waves, that phase difference between the 2 points on a stationary wave are either in phase or out of the phase. Now, when you talk about a phase difference, because this wave and this wave and this wave, they may have different, because they are different waves. So each wave is basically either in phase or either out of the phase. So points between the nodes are in phase with each other. Within, remember that point between the nodes. No, this is a node and this is a node. So whatever points are there, all are in phase. That's what the point is. Each point is in phase to the second point, but within the node. Now, the second point is very interesting. Point that have an odd number of nodes. Odd number of nodes are 1, 2, 3. This is odd number of nodes. Between them are out of the phase. Now, whatever points are here in between, they are out of the phase. Like this one is not in phase with this one, or this one, confusion. So if there is an odd number of nodes, then the points between of the nodes between them are out of the phase. But if they are even, they are in phase. Okay. We will explain this further once the thing will proceed. You will see that at this point it looks a bit difficult, but as we proceed, you will be understanding this. What exactly is this? While we have a small derivation as well. For the time being, just you need to understand that in phase is a point where in two different waves, the point will be at the same position. Same like we are talking about progressive wave previously. All right. Now let's proceed further. Now, Check this out. A stretched string used to demonstrate a stationary wave as shown. Which row in the table correctly describes the length L of the name of X and Y? Now tell me which one it is.
Are these all the options?
Yeah, 4 options altogether. You have to select either A, either B, either C or D. Which one is right? A, B, C, D. Which point is Y, by the way? Node or antinode?
It's an antinode.
Antinode. So if Y is antinode, you can only see Y antinode in part A and part B, because second point they show it as nodes. So it can be either A or it can be either C. Now, what about the wavelength? Will that be 5 or will that be 2 whole number 1 by 2 waves?
2.5.
Absolutely. This is the right answer. That's it. It means you understand what stationary waves are. So basically, this is 2 whole number 1 by 2 waves. So correct answer is C, I think. Yeah. Okay. Again, in the end, what nodes are? A point of minimum or node disturbance, antinodes point of the maximum amplitude. Now there is a small derivation, I think, to the next topic in the formation of, let me just check it out. Is that the one? Okay. This is the formation topic. It's not that. Okay, it's in there, harmonics. Yes, this is the one. Now, first thing is, let's see the formation of the wave first. What is the principle of superposition? How does one wave actually superimpose or superpose on the other one? When 2 or more waves with same frequency arrive at point, the resultant displacement is a sum of displacement of each wave. Now, what does it mean is, let's take an example. This is one wave. This is another wave. When these two waves combine, what do you think? The displacement of the waves increases or reduces? Resultant one increases. So resultant will be like this. It means that that type of superposition is called as interference of constructive type or constructive interference. When two waves have same frequency and amplitude arrived at a point, they superpose either in phase, either in phase causing constructive interference, the peak and the trough lines up both waves. Now, this is very interesting. If you see these two waves, crust will fall on crust and trough will fall on trough. Am I right?
Right.
This thing is called as in phase. They are in phase. Crust will be falling on crust and trough will be falling on trough. So if these two things are in phase, that will be called as constructive interference. Now the second example is, one wave is that, the other wave is that. Now crust will fall on trough and trough will fall on crust. If this thing happen, That type of interference is called as destructive interference. Okay? Where resultant amplitude will be 0. Let's take an example here. Check it out. It was a constructive interference. Why? You will have two waves and the resultant is 2A. The displacement become 2A. So interference is constructive interference. On the other side, let's see the destructive interference. You will have no amplitude or displacement left because both cancelled each other. So that interference is called as destructive interference. We have a complete interference topic, which we will be discussing once we finish with this. Any questions?
No,
No.
Yes, Zoha. Any questions?
no, this is fine.
Good. Now the principle of superposition applies to all type of waves, transverse and longitudinal waves. So this happens to both of them. So how can we summarize it? When this stationary wave is formed, two waves traveling in opposite direction along the same line with same frequency. The wavelength must have the same wavelength, a similar amplitude, a result of superposition, a resultant wave is produced. Like that. Okay.
How would this look like in a longitudinal wave?
This will apply like in that case, your compression will fall on compression, or your compression will fall on rarefaction, and your rarefaction will fall on compressions. But it's difficult to visualize it. That's the reason for visualization, we normally use transfer wave. It's easy to visualize it.
Yeah.
Otherwise, it's difficult. Okay, now you tell me one thing. If I ask you, what is the distance between two consecutive nodes or antinodes? It's already shown if you see that.
Half wavelength.
Half wavelength. It means if question asks you, what is the distance between two consecutive nodes or antinode, it is half wavelength. And what about distance between one node and its antinode? Consecutives?
Quarter wavelength.
Yes, it will be 11/4. So at nodes, the waves are antiphase, meaning destructive interference. This causes two waves to cancel each other. Now, it's more pronounced that at antinode, when there is no displacement, it technically means it is a what do you call it? Destructive interference. All right. And when you're talking about constructive interference, it's called antinode. Okay.
Okay.
Now you can see the constructive interference and the destructive interference. What about the second one? You tell me two waves, one crust fall on the other trough and one trough fall on the other crust. So it's a destructive interference in the second diagram. While in the first diagram, here, it's a constructive interference. This one. This is constructive interference, while the other one is destructive interference. All right?
Okay.
See that. Okay, now if you see that, wave is in antiphase, destructive interference. Now decreasing phase difference. Now check this out. There is a phase difference, but it's not 101% the crust fall on trough. Small movements. Here, this is a pure wave in phase, constructive interference. This is a wave, crust fall on a crust, trough fall on a trough. So there are three conditions they showed us. One is a pure destructive interference, one is a pure constructive interference, and here it's not 101% the same phase. I mean, you can say here phase difference is 0. At this point, the phase, sorry, let me have my pen. At this point, the phase difference is 90 degrees. Here, the phase difference is 0 degrees. But here, it's somewhere in between 0 and 90. So it
Okay.
depends, right?
I find it hard to find the phase difference, the path difference.
But you don't have to actually find out the difference or anything. It is just to memorize it because it is not.
No, we do in our board, we do get questions where they give you two waves that are not exactly in or out of phase, but they do have a path difference, and you have to find their difference in angles,
But you can do that.
typically radians.
We will do those questions, and that happens like this. For example, you will actually draw a wave like this. Let's suppose this is 0. This is, let's suppose, 90. This is something. This is something. All the angles are given to you. And one more wave is there, like this. And their angles are given as well. Now, if you check this out, I told you previously, it's already half wave passed. So you have to see the difference between this and this. Crust and crust. It's 0 point, and if you check here must be some angle 90, let's suppose. So you will simply subtract 90 from that angle and you will find the phase difference. It depends on wave to wave. You always find out the difference between the first point where the wave is and in the second wave where this wave is actually from where the point is actually started. Because in this one, half of the wave is already started and the actual wave is started right at this point. So very easy to find out because once you draw that, it will be easy to do that. So once we inshallah finish with this all, we will do the past paper question and then I think so you will be able to understand and draw that as well. It's not difficult. It look like difficult because it's a bit rough, tough type of topic. It's nothing enjoyable in this, but we have to do it because it's in our course. All right. So once we come to the question answer from the past paper, we will do that. But do you understand how to find out the phase difference?
Yes.
It's not difficult, I tell you. It trust me, it's easy. Okay. Now, yeah, you're saying
Now, wait, you know how you're using the nodes to find the difference? I've seen something like this. There's a point X and a point Y, and they're randomly placed. They're not even on a crest or a node. Can you do it
you mean this
somehow?
one? You mean that one, for example?
On the same,
Okay, like this one. And one is like this. Something like that, right? Like that?
yeah,
What's the problem in this? Check it out. What is the angle here? It's 0 degree. Check this angle. That is your phase difference. See,
okay.
whenever the wave is drawn, remember that they are plotted, the points are plotted on angles, right? So once you know the angle values, you can simply find out the difference between the first point, which are started at certain points. Because here on a single line, it's easy to actually see that because that phase difference will not be changed. This will be continuous for all the points. If they are on different, you know, graphs, then it's difficult to judge. But on a single graph, it's very easy to judge it. Just see from where the first wave is started. If one wave is started from 0, other wave is started from some other point, that difference will be your phase difference. It's very easy to find out the wave difference. Very easy. If you have any question, I want you to bring that. We will discuss it. All right.
Okay.
Okay, now this one is actually sorted. Now let's find out the small calculation related to this. Now, what is meant by harmonics? And there are some more topics in it. For that one, actually, I got some notes for you, very interesting notes. Check this out. Let's suppose we are actually making a wave here. First thing first. Now, what exactly it is? If you see that, wait, let me see. How many waves are there? One
Half.
complete. You can call it half, or can I say that lambda equal to 2L? Can I say that?
Yeah.
Because actually 2L's are combined to give you 2L's are actually fine to give you lambda. Now this is the case when there is one loop, right? Or in other words, you can say that L is equal to 1 by 2 lambda. Now when in length of a loop, I mean in the length of a string, you will have one loop only. You call this frequency as a fundamental frequency. Fundamental frequency means one loop. This fundamental frequency is also named as first harmonic. First harmonic means one loop. If I talk about lambda 1 wavelength, it will be 2L. Or can I say 2 upon 1L?
Yeah.
I'm saying that there is a reason. Now another thing, which is very, very important. Now let's, for example, if instead of one loop, we will have two loops. Can I say that now that because lambda means it will be equal to L, because actually it divides into two. So it will be L. Or in other words, you can say this is the one complete length, and you will have one complete lambda, one crust and one trough. So can I say that lambda 2 is equal to L? Or in other words, I can say that lambda 2 is equal to 2 upon 2L. Can I say that?
Yeah.
If
Yes.
I say that, this is your second harmonic. So second harmonic is this one. Let's talk about n is equal to 3 if there are 3 loops. How many waves are there? 1 and 1.5. So technically speaking, I can say that lambda is equal to 2 by 3 L, or or I can say that L is equal to 3 by 2 lambda 2. So basically, that is your lambda 2 by 3. Why 2 by 3? Because 1 and 1.5 and 0.5. 1 and 0.5 is how much? 3 by 2.
Mm.
So now if you see the thing, what I'm actually wanted to tell you. Firstly, it was 2L is equal to lambda. Then it was lambda is equal to L. Then it was L lambda is equal to lambda is sorry, lambda is equal to 2L, then L, then you will have lambda is equal to 2 by 3L. Are you noticing one thing? Now check this out. In the first or fundamental loop thing, you will have lambda is equal to 2 upon 2L upon 1. That is lambda 1. Or you can say the lambda of one fundamental frequency. When there were two loops, it's changing into 2L upon 2. Then it was lambda 3, it becomes
3.
yeah, it will be 2 upon 3 L. What if it's lambda 4? It will be 2L upon 4. If it's lambda 5, it will be 2L upon 5. So technically speaking, if you see that they are moving in a certain pattern, it means that for standing waves, if you know the length of the string you're working on, you can very easily find out the lambda or the wavelength. And once you find the wavelength, you can very easily find out the velocity. How do you do this? I will let you know. And then we will solve one or two numericals. I have that numerical as well. Now check this out. If you see that in general, where is it? Let me rub that. If I ask you the generalized form of this lambda, what the formula will be? These number of loops, if I provide you, you can simply find out the lambda of those loops. How? Very simple. Lambda n will be equal to 2L upon n. This is the generalized form of the wavelength. You place the n value in there and you will find the lambda of that particular wave. All right.
Mm.
Any problem in this?
No.
All clear? Okay. So first of all, we found out the generalized form. Now what our target is? Our target is to find out this is the generalized form. Now we need to find out the frequency. And what is frequency equal to? The frequency is F is equal to, now what F is equal to? V is equal to F into lambda. We have seen this formula a few minutes ago. Now what is frequency? Frequency equal to V upon lambda. So V is V and lambda value is this, which is 2L upon N. So frequency will be equal to N V upon 2L. This is the frequency for nth loop. So by any chance, if they ask you what is the frequency of second loop, you will simply place the values, put the length of the string, and you will get the answer. This is one of the formulas. Understand? Yes, hello?
Yes.
Any problem in
No.
this?
Oh.
Too much problem?
No.
Okay. One more thing. First harmonic is the first fundamental frequency as well. Second harmonic is the second after first fundamental. We called second harmonic as first overtone as well. There is a word called overtone. First one is first harmonic. Second one is definitely the second harmonic. Third one is the third harmonic. But second harmonic is also called as first overtone. Then the third one will be the second overtone. So overtone means right after the first fundamental frequency will be considered the first overtone. So both the terms are used reversibly, I mean, in a certain way. First one is the first harmonic, second one is the second harmonic, third one will be the third, and the fourth one will be the fourth. But here, as far as overtone is concerned, first one, after first one, the second harmonic will be the first overtone. The third harmonic will be the second overtone, and the fourth harmonic will be the third overtone. So students understood?
Yes.
Okay. Now let's see how they use the formula here. The question is here now, and let's see. This is the formula. The velocity of wave can be found using V is equal to Ft mu. Now, this is a generalized formula. They give you the formula. Well, the tension. This is the formula. They already give it to you. You just need to put the values in, and that's it. Now, what point actually I want you to actually do that? What is the question? Check it out. Let me just rub that. Sorry. Okay. Now, if you see the question, the standing wave depending on the boundary condition. The second one, if you see that, they say impossible mode, and the first one is possible mode. Why is like this? Can you tell me the reason? The first one is limited to 2 points, while second one is open from 1 point. That is the reason it is impossible. Okay? Standing wave should have a closed conditions. Then and only then you will be able to solve it. Now check this out. For example, if you've been given the length 2L, can you find me the wavelength while there is a single loop? We already seen some formulas. What is the formula? 2L upon 1. What is the wavelength? Can you check it out?
So that the wavelength is
4 meters.
4.
What about when n is equal to 4? Yes.
I'm not sure.
Just place the values. That length is given 2. Place the L is equal to 2 here, 2 to the 4. 4 divided by 4, because generalized formula was 2L upon n. You just place the value into 2 into 2 is 4 divided by 4. So 4 and 4 will cancel, and you will have a wavelength 1 meter. So you can find out the wavelength by simply placing into the value. Check it out. Initially it was 4. Then it's 2. Then it's 1.3. Are you noticing one thing? That's the reason I showed it to you, that your wavelength is reduced as the number of loops are increasing.
Yeah.
So it means more the number of loops are, less will be the number of, less will be the lambda b. More loops, less wavelength. And one more thing, in that case, the frequency will also be changing. So because frequency is equal to velocity upon lambda. Because lambda changes, so velocity, velocity remains the same. You tell me, if lambda is basically reducing, frequency will be what?
Increasing.
Increasing. Now let's see these. So F1 is 14.29, F2 is 28.58, and F3 is equal to 42.87. Are you looking at these? Frequencies are increasing. At this point, I want to tell you another formula which is very, very important here. F2 is equal to 2F1, F3 equal to 3F1, or a generalized one, Fn is equal to NF1. So if you know by any chance the first frequency, or you can say fundamental frequency, they will ask you any frequency and you will find out. Copy these one as well, because I'm asking you a question now here. I want you to solve it. Let's suppose your F1 is same. Check this out in putting the formula into F2 is equal to 214.29. Check it out. Is it the same value? 28.58?
28.58.
Right.
It's the same.
It's the same. It should be. So it means that if you know F1 here, you can simply multiply it with the number of waves and you will get it. I'm asking you to find me the value of, or find me the frequency of fifth overtone. Word is fifth overtone. Fifth overtone. Fifth overtone means what will be the value for N here? Fifth overtone?
5.
No, that's what the tricky.
4?
6.
Oh.
Because I told you overtone start from the second frequency. I mean, N is equal to 2. N is equal to 1 is the harmonic. N is equal to 2 is the harmonic. First harmonic is N is equal to 1. Second harmonic is N is equal to 2. Third harmonic is N is equal to 3. N is equal to 2 is here you start with the first overtone. N is equal to 2. Third one is the second overtone. Fourth one will be the third overtone. So when I say fifth overtone, technically speaking, this is N is equal to 6. If you know 14.29, what will be F6?
85.74.
Yes, hertz, right? So now you actually found out that how the thing's going to be. If you know the frequency, we have also find out how actually we can find out the lambda. If V is given to you, you simply divide lambda 1 with V. And once you divide it, you can find out frequencies. Any question till now? This is all standing wave. There is one more formula in that, and that is up. That is finished. No more standing waves. Quickly go through that. I know it's a bit hectic, but and then I think we better finish it because it looked like you are all exhausted.
Yeah, that's very true.
I knew that because is a rough topic actually. So what we have finished in this today's lecture, we have finished that what are progressive waves. So again, one by one, Alicia, so that we will finish it up. What is the first difference between the progressive wave and the stationary wave? You already told that one wave is storing the energy, the one with the standing wave.
For progressive waves, all the points have same amplitude.
Absolutely.
Well, for stationary waves, they have different,
it depends on the superposition of the waves, right?
yeah.
One is storing the energy and one is passing the energy. What is the other points?
In a progressive wave, they have crests and troughs, but in a stationary wave, they have nodes and antinodes.
Rather than saying crust and trough, you say no antinodes and node because there are compression and rarefactions as well. So rather than saying just say no nodes and antinodes, and here you have nodes and antinodes. What about the next point? Velocity or speed? Yes, what was it?
For stationary waves, each point oscillates at different speeds, and for progressive waves, the wave speed is the speed at which the waves move through the medium.
Absolutely. Let's quickly go through that and you will just, I think we have already sorted out. Now this one is the wave speed is the speed at which the wave moves throughout the medium because it moves throughout and it's just an oscillation at different speeds. The second point is all the points which are in phase are coming after 1 lambda, which is within 0 to 360. These phase of points within one wavelength can be between 0 to 360. On the other side, the points between nodes are in phase. The points on the either side of the nodes are out of the phase. Then we have seen some definition related to nodes and antinodes. Nodes are the point where no vibrations. Antinodes are the point where there are maximum displacements. Then we have gone through quick small derivation related to a stationary wave, which shows us that what will be the wavelength and what will be the velocity and what will be the frequency formula for that. There is one more formula in our course quickly. I just want to, go through that and then we'll finish this. Interference, stationary waves. Wait a second. Somebody, okay. I think this one is the case. Okay. That formula is the same thing, but third overtone and the fourth one is the same. See here, the point which we are talking about is twice t. Okay, that one is the same thing. I'm not actually interesting in this, but I am interesting about is the one interference, I believe. Let's see. No, not this one. If velocity is given as v is equal to root tension upon mu, where t is a tension and mu is a mass per unit volume, what will you do? You find out the lambda, then v is equal to frequency lambda. So frequency will be equal to v upon lambda. So the formula becomes, I'm talking about F1 frequency. It will be 1 upon 2L root T upon mu. Check it out. So it will be, these are the values, let's suppose. So first frequency, second frequency hertz in mean, you take it. So it will be, these are the calculations you see. Mu means mass per unit length. You place the values into that and you get the hertz of that. We will continue with this calculation tomorrow. Then it will be much more pronounced and much more easier for you. I think it's too much to absorb for you. You better go through this all and inshallah we see you tomorrow with all the standing wave and then we'll proceed further. Is it right?
Okay.
And the
Okay.
recording I am uploading right now. Okay. If you want to go through the recording, you can, right?
Yeah.
Okay, then take care. Bye.